Hello everyone, welcome to our presentation. Our project is on shoreline restoration and resilient infrastructure in Norfolk. Our team has 5 members: Carol, Wenny, Morgan, Marco, and Catherine. And our sponsor is Wetlands Watch. Our advisors are Dr. Sample and Dr. Sridhar. We received additional mentoring from the Elizabeth River Project, ODU, and the Lafayette Wetlands Partnership. This project is a Wetlands Watch collaboratory project funded in part by RISE. Our problem involves a site in Norfolk, Virginia, located near an ODU building, Rogers Hall. Our design involves the shoreline, parking lot, and boardwalk shown on the map. The shoreline borders Colley Bay, a tributary of the Lafayette River. This is the shoreline site viewed from the ground. The shoreline is eroding and plants are unable to grow on the low tide mudflat due to the flow of water coming from the nearby outfall. The red circle outlines the existing bulkhead, which is deteriorating and not protecting the near shoreline from erosion. The parking lot has an area that is regularly flooded and contains reed grasses, or Phragmites australis, an invasive species growing near the parking lot. The reeds caused sediment to build up and trap water from the high tide in a pond in the parking lot. This has been making the area unusable for parking as well as a university liable for damages to vehicles. The current boardwalk is old, slightly deteriorated, and is not equipped to adapt to sea level rise. Plants are not able to grow along the shore due to shading caused by the boardwalk, and the shoreline is eroding from inland due to the sheet erosion from the parking lot.
Listed here are the constraints and criteria that apply to our design. And there are 3 standards we have been used for our design. To prevent the shoreline erosion at our site, we are proposing a living shoreline. A living shoreline is a coastal edge that is protected using natural materials such as plants, sand, or rock. We plan to turn the current mudflat into a graded slope filled with sand, which will be planted with marsh plants that will stabilize the shoreline. We plan to largely use our oyster castles to protect the shoreline from the wave energy, which coming in from the bay. Due to a large amount of water coming from the outfall, we plan to use the riprap to reduce the water velocity along the outfall channel. For the outer edge of the shoreline near the outfall, oyster castle seal will be used to protect the marsh and shore from wave energy. There is less erosive energy due to the waves at the upper part of the shoreline. So we will just grade and fill bank with sand, plant vegetations, and use a temporary biodegradable Carlock cell to protect the shore until the vegetation grows.
This slide shows a profile view of the oyster castle sill we are proposing. The oyster castles themselves are interlocking concrete blocks that will act as a surface for oysters to grow on. For our design, the castles will be stacked 3 high and they will be arranged in a diagonal layout, which will help to break up waves that collide against them. Behind the oyster castles, we plan to build up the shore with sand fill at a minimum 10-to-1 slope. A 10-to-1 slope can usually provide a wide enough area to plant vegetation and is gradual enough to help dissipate energy as waves come onto the shore. We propose planting smooth cordgrass in the low marsh, which is located on the shore between the mean tide level and high tide level, as seen in the diagram. Spartina alterniflora, or smooth cordgrass, is commonly used in living shorelines because it is a hardy native plant that is effective for erosion control and can tolerate inundation by brackish water during high tides. This slide shows a profile view of the section of the living shoreline that will be supported by core logs. These logs, made of woven coconut fiber, hold in the sand and provide temporary protection from waves while the marsh plants are growing. They will biodegrade over the course of 3 to 5 years, after which the vegetation will have established enough to be able to stabilize the shore. Our final parking lot design involved redrawing parking spots and converting the flooded area to a riparian buffer. A riparian buffer is an area of vegetation that grows near a stream or water body. The plants in the buffer act as a natural barrier between the stream and other land uses that filter sediment, nutrients, and other pollutants from stormwater runoff. It also provides shade and wildlife habitat. Our design proposes to remove the impervious area of the parking lot that is currently flooded and unusable, and remove the invasive species currently there to return it to a natural vegetated state. By redrawing the parking spaces, we were able to maintain the same number of spaces.
The first boardwalk solution consists of modifying the existing boardwalk to incorporate composite grate decking to allow sunlight to pass through to the living shoreline and plants below. During our site visit, we observed the boardwalks, such as the one pictured on the left, which used the concept of bringing the boardwalk out into the water to allow light to get to the plants that will be planted along the shore. Our second solution involves a redesigned boardwalk that combines this idea with the graded decking to allow sunlight and water to pass through to the floor of the boardwalk. We also plan to have the boardwalk height be 1 foot above the projected level of sea level rise so that it will be usable for longer.
This design is similar to Concept 2, but is a lower impact version requiring less materials and having a smaller footprint. Having it go straight out into the water reduces the amount of shade that will be cast by the boardwalk onto the plants in the living shoreline. The floor would be made of the same graded decking and raised to the same height as the design in Concept 2. A 24 by 18-inch educational sign was designed to be placed within the boardwalk to inform local residents and visitors about living shorelines. Thank you for listening.